Hello dear students, welcome back. Today we are going to discuss about magnetic field due to a current carrying circular coil. In the last class we studied about magnetic field due to a current carrying straight conductor, isn't it? Only one change, now it's a circular coil. So for this we consider a circular coil, we take a circular coil and we place it in a cardboard as like this, making two holes in the cardboard, and we place the circular coil. It will be a wire, so we can easily take through this hole as like this textbook. If we make two holes here, we can place a circular coil using this, isn't it? Now see here, it's connected to a potential difference, that is a battery. Here there is a rheostat, key is in the on condition, current will flow in the direction from positive to negative. So this was the experimental arrangement. Actually this experimental arrangement was done by Ampere after Easted discovered that there is a relationship between electricity and magnetism. Ampere conducted some experiment based on this. So for that he considered this circular coil, and that is placed in the cardboard. Obviously if current flow through the circular coil, it must act as a magnet, isn't it? That we studied already. So for finding the direction of magnetic field, if there is a if the conductor acts as a magnet, there will be a magnetic field. So in order to find the direction of magnetic field, what Ampere do is put some iron fillings over this cardboard. Small iron fillings, means filings, very small iron particles that will be attached to the magnet if you are dragging through the soil also. So such type of very small iron filings were spread over this, and now he on the key. What happens? This magnetic particles or iron fillings start to arrange in circles around this coil. So it start to arrange in circles here also, around this coil also it start to arrange in circles. And it was like this. It was more intense in the center due to the magnetic field due to two coils. Here, see here, there is one end here. Due to this end, there is a magnetic field around this one. And here in the right side also there is a magnetic field. So when we come to the center, the magnetic field seems to be more strong because due to two concentric circles. Here there is one concentric circle, here there is one concentric circle. This concentric circle means concentrated to a point, this point. So due to these two circles, they coincide together, some of the lines coincide together in this region, and this region magnetic field found to be very strong. So this was the experimental thing or the experimental structure that conducted by Ampere. So from this experiment, Ampere noted some of the conclusions. That conclusions is very important. First one, he saw that there were two concentric circles around the conductor whenever it passes through the cardboard. So there were two concentric circles were found, and the magnetic field lines is found to be in the same direction in between these two concentric circles. See here, the direction of magnetic field was found to be unidirectional, means they were in the same direction. At the same time, one other thing he noted that when the current flows in one direction, here see the current is flowing in this direction, and on that line magnetic field direction is found to be this wise, that is this anti-clockwise, and here it is found to be in the clockwise. So one of them is opposite to the other concentric circle. The direction of one of the concentric circle is opposite to the other concentric circle. At the same time, in between two concentric circle, the direction of magnetic field is found to be in the same direction. Even though it is in the anti-clockwise and it is in the clockwise direction, see, this is in the anti-clockwise direction and this is in the clockwise direction. But even though if it is so, in between these two concentric circles, see the direction, they are all unidirectional, isn't it? They are all in the same direction. And also he found that magnetic field is found to be more strong in the center of the circular coil. Center of the circular coil is here, and the distance from the end to the center is the radius. So it is found to be more strong in the center, and towards the center the magnetic field lines is found to be straight and parallel to each other. They are straight and parallel to each other. So here magnetic field is uniform and non-uniform here, but magnetic field is uniform in the center. At the same time it's also very strong in the center due to the presence of two concentric circles. So both effects come on this center. That is why it become more stronger here. So Ampere noted these conclusions from the setup, and also he found an easy method for finding. He told that if a current flow in clockwise direction and anti-clockwise direction, accordingly magnetic field also changes. So magnetic field changes due to the north pole and south pole. If there is a change in the north pole and south pole, they may change. See here, he found a easy method for finding the pole of the magnet. This circular coil will act as a magnet, isn't it? Every magnet has a north pole and south pole. That's clear. Every magnet has a north pole and south pole. So obviously, if this circular coil is a magnet, if it acts as a magnet, it should have a north pole and south pole. How to find the direction of this magnet? How to find the north pole and south pole of a magnet? For finding that, he found an easy method. Okay, so draw a circular coil and mark S like this. See here, okay, if the current flows in this direction, see, I mark a S here, S, and I marked two arrow marks like this, and I mark the same thing here also, this arrow mark here also. So what happens? See, the current is flowing in the clockwise direction. If the current flows in the clockwise direction, that means this part is the south pole. Yes, S for south pole. Now for north pole, write the letter N and draw a circular coil. It's not full circle, but almost it's not a semicircle also, almost a full circle. Okay, so we have to draw like this and mark two ends like this. Now we can mark here like this, and same thing we can mark here. The same arrow mark we mark here, the same arrow mark we mark here. So what is the direction of the current flow? Current flow through the coil is in the anti-clockwise direction like this. This anti-clockwise direction. Clockwise direction is this one. This one is clockwise direction. So whenever the current flows in the anti-clockwise direction, that portion is the north, that portion acts as the north pole of the magnet. Is it clear? It's very easy. See, to find the direction, to find the pole of a magnet, we understand that a circular coil acts as a magnet if current flows through the circular coil. These points only you have to be very clear with. The circular coil acts as a magnet if current flows through the magnet. And if it is a magnet, there should be a magnetic field. The magnetic field is found to be in two circular concentric circles. And in between these two circles, magnetic field is found to be in same direction. towards the center, it's straight and parallel, that indicates uniform magnetic field. And the lines in the center are more intense, that is due to the presence of magnetic field lines due to the two concentric circles. That's why magnetic field is more strong in the center. Now, to find that if it acts as a magnet, there should be a north pole and south pole for this magnet. To find that, there is an Epc method, that is, if current flows in clockwise direction, that part is south pole of the magnet. If current flows through anti-clockwise direction, that part acts as the north pole of a magnet. So I will show you if I have something. Okay, let me show with this. So here, let it be like this. So imagine this is a circular coil. Okay, half portion of circular coil. Okay, right. Now, firstly, we can consider that the current is flowing in the clockwise direction. If the current flows in the clockwise direction, what happens is this part acts as the south pole. Now imagine the back side. See, current is flowing from this part to here. Imagine the back side of the magnet. From where to where the current is flowing? From here to this one. Okay, it's written 25 here. So this is the end portion. We can understand that by here, looking this. Now bring here. The current is flowing from this part to here. 25 is written here, isn't it? From here to here. What happens? Current is flowing in the anti-clockwise direction. So this part will be the north pole. Do you understand it? If this circular coil acts as a magnet, the front portion will act as the south pole and the back portion will act as the north pole. Is it clear? I hope it is clear. Once more, to find it, the south pole and north pole, there is an easy method. Just draw a letter S and draw a circle around this and mark two endpoints, and coinciding this point just above that we have to draw two arrow marks. So if the current is flowing in the clockwise direction, if the current I is in the clockwise direction, that indicates south pole. If the current is in the anti-clockwise direction, that indicates that part is the north pole of the magnet. So these are the properties of magnetic field due to a circular current carrying coil and the direction of magnetic field. Now to the last one, magnitude of magnetic field. So while conducting the experiment, there was a rheostat in this figure, isn't it? What is the rheostat used for? Changing the resistance of the resistance in the circuit. If the resistance is increased, current flow will be decreased for that. So by doing that, we find that whenever the current is increased, magnetic field is also found to be increased. That's magnitude of magnetic field is directly proportional to the current flowing through the conductor. That was the first inference we got from the experiment. Second one, if we increase the radius, our circular coil was this much size only. If we increase the radius, that makes a decrease in the magnitude of magnetic field. Therefore, we can write it is inversely proportional to the radius. Here it R to be the radius. So directly proportional to the current flow and inversely proportional to the radius. Now one more thing. Instead of one coil, what happens if we bring 2, 3, 4 coils? What happens when we increase the number of coils? When we checked this out, we found that magnetic field increases with the increase in number of turns. Number of coils. If the number of coils or number of turns are increased, that make an increase in the magnetic field, magnitude of magnetic field. So combining these three, we can write B is proportional to I and N in the numerator. I N divided by R. So magnetic field is proportional to I N by R. I is current flow, N is the number of turns, R is the radius of circular coil. Hope this section is clear for you. Thank you for watching. Have a nice day.